Next, we'll start talking about the convex problems. So what are the convex problems? To describe these problems, we need to define a convex function first. So before, we already discussed the definition of a convex set. Convex set, remember, was a set such that for any 2 points from this set, the line segment that connects these 2 points must completely belong to the set, right? So this is a convex set. So, but what is a convex function? So a function f is convex over a convex set, say denoted by x capital, if for any 2 points x and y from this set x, f of alpha x plus 1 minus alpha y is less than or equal to alpha times f of x plus 1 minus alpha times f of y for any alpha between 0 and 1. So let's illustrate this geometrically using a function of one variable. Convex function looks like this, okay? So say this is x, and here we have y. Alright, so then this will be f of x, and this is f of y. The condition we have here, it says that f of alpha x plus 1 minus alpha y is less than or equal to alpha f of x plus 1 minus alpha f of y, and this is the case for any alpha between 0 and 1. Let's see what this means geometrically. So here we have a point x f of x, here we have a point y f of y, and now let's consider an arbitrary alpha between 0 and 1, and let's consider the point which is given by alpha x plus 1 minus alpha y. So for example, this could be a point somewhere here. So let this be alpha x plus 1 minus alpha y. Now, what is f of alpha x plus 1 minus alpha y? So this will be the value of our function f right here. Okay, so this point. This gives me f of alpha x plus 1 minus alpha y. So, and what this condition tells me, that this f of alpha x plus 1 minus alpha y is below, or at least no higher than alpha f of x plus 1 minus alpha f of y. So what does it mean geometrically? It means that if I draw the line between the points x f of x and then the point y f of y, then alpha f of x plus 1 minus alpha f of y will be located between f of x and f of y exactly here. It will be the value for this function defined by the line, right, that corresponds to the argument alpha x plus 1 minus alpha y, so it will be here. Essentially what it tells us is that this point that corresponds to the value of the function f of x, right, so will be below the point that corresponds to the value for this linear function that connects x f of x and y f of y. Alright, so essentially if I draw the line between any 2 points like this, then my line here will always be above part of the function corresponding to this line segment. Okay, so this is what it means geometrically. So now that we have the definition of the convex function and the convex set, we can define what a convex problem is. So if I look at the problem of minimizing f of x subject to x is in x, this is a convex problem if x is a convex set and f of x is a convex function over x. This is the definition of a convex problem. It consists of 2 important parts, so both parts are equally important. Okay, so it's not just the objective that must be convex, but the feasible region must also be convex. Convex problems play a very important role in optimization, and one of the reasons for this is the fundamental property they have that we'll state next. Okay, so we'll state it as a theorem. Any local minimizer of a convex problem is its global minimizer. Okay, so this is a very important property of convex functions, and we can actually show that this property holds. The proof of this is relatively easy, so we'll go over it. Let's look at the problem of minimizing f of x over the set x, where f of x is a convex function over x, and then x is a convex set. Okay, so what we need to show is that if x star is a local minimizer for this problem, then from this we can conclude that x star is a global minimum. So proof. Okay, so let's take an arbitrary local minimum x star and assume the opposite of what we are trying to show. Assume that it is a local minimum that is not a global minimum. So then what we need to do is we need to get a contradiction with the fact that x star is a local minimum, right? So if we get that contradiction, then this will show that it is impossible to have a point x star which is a local minimum but not a global minimum. So how do we get the contradiction? We assume that x star is a local minimum but not a global minimum. So if it is not a global minimum, then there exists some point where the objective is actually better. Let's denote it by x hat, which is in our set x, such that f of this x hat is less than f of x star. Right? So this is what the fact that it is not a global minimum means, right? So it means that there is a better point. If there was no better point, then it would be the global minimum, right? Assuming that such a point exists, what we'll do next, we will start at x star and we'll move towards this point x hat along the line segment between x star and x hat. Okay, so let's consider the point between these 2 points. Let's denote it by y, which will be alpha x star plus 1 minus alpha x hat, right? So this is a convex combination for x star and x hat, right? So we can use it to represent a point between these two. So this is our point y. So, and then what we'll do, we will use the convexity property for our function, for our problem, to show that this point y will have a better objective than the point x star. Okay, so and then, you know, since we can select alpha arbitrarily small, we can make this y arbitrarily close to x star and show that there is no neighborhood for x star where x star is actually the best point. So therefore this contradicts to the assumption that x star is a local minimum. All right. Okay, so but first, because y is a convex combination of x star and x hat, and both x star and x hat belong to the set x, right? And the set x is assumed to be convex, it means that y must also belong to the set x by the convexity of x, right? Now let's look at f of y. So f of y is given by f of alpha x star plus 1 minus alpha x hat. Now we can apply the definition of convexity, right? So because the function f is convex, this f of alpha x star plus 1 minus alpha x hat must be less than or equal to alpha f in x star plus 1 minus alpha f in x hat. Okay, and then remember we assume that f of x hat is in fact less than f of x star. So this part here is less than f of x star. And now we use this assumption to show that this is actually less than alpha f of x star plus 1 minus alpha f of x star, which is just alpha f of x star plus 1 minus alpha f of x star just gives us f of x star, right? Okay, so what we have, so we started with f of y, and we have shown that it is less than f of x star, right? So we have f of y is less than f of x star. So, and again, we can select alpha for y to be within any close proximity of x star, right? So therefore, this shows that there is no neighborhood of x star where f of x star is less than or equal to f of x for any x within this neighborhood, right? So therefore, x star cannot be a local minimizer. So, but this contradicts the assumption that we have here. We started by assuming that x star is a local minimizer, right? So we obtained the contradiction. So therefore, we cannot have a local minimizer that is not global at the same time. Therefore, every local minimizer for a convex problem must also be a global minimizer for this problem. All right? So we see that convex problems are very special. To find the global minimizer, it is sufficient to find the local minimizer. So let's say if I have a non-convex problem, so say if I have something like this here, so this is a non-convex problem, right? So we have a bunch of local minimizers that are not global, right? So we have only one global minimizer here, x star. Whereas for convex problems, everything is relatively simple, right? So as soon as I got a local minimizer, it must be a global minimizer. So it will be the best point, not only locally, but globally. So this puts the convex functions in a special category, but we will actually show even stronger properties for convex functions. We can actually show that it's sufficient not to just find the local minimizer, but it is sufficient to find a point that satisfies the first order necessary condition or the stationary point in order to show that the point is in fact a global minimizer. However, to establish this fact, we need a result which is called the first order characterization of a convex function. The first order characterization of a convex function tells us that a continuously differentiable function f, and the continuously differentiable function is a function that has the first order derivative, which is a continuous function also. So the continuously differentiable function f is convex if and only if we have the following. For any x and y in the set X, we have f of y is greater than or equal to f of x plus the gradient f x transpose times y minus x. Okay, so we are talking about convexity of f over the set X, of course, right? A continuously differentiable function f is convex over the convex set X if and only if for any x and y from X we have the following inequality. So we have f of y is greater than or equal to f of x plus the gradient of f of x transpose times y minus x. Okay, so let's look what this means geometrically. Let's look at the convex function. So this is our point x and this is our point y. This is a one-dimensional case, and the gradient in one-dimensional case is just the first order derivative. Geometrically, this means the slope of the tangent line for f at the point x. What we have in this inequality, we have f of y. So this is our f of y, right? Is greater than or equal to what? F of x. So this is our f of x plus gradient of f in x transpose, so it becomes f prime of x, right? So f prime of x is the slope of the tangent line at the point x, right? Let's draw the tangent line here. The slope of the tangent line multiplied by y minus x, and y minus x is what? Is the length of this interval here. So if I multiply the slope by y minus x, then what we get will be the length of this interval right here. Okay. This essentially is the growth that we have for the tangent line, right? And f of y minus f of x is the growth that we have for the function. Okay. If I add f of x and the f prime of x times y minus x, which is this interval here, the length of this interval, right? So then what I'll get will be this value here. So this is exactly f of x plus f prime of x times y minus x, right? So this is essentially the right-hand side of our inequality here, and f of y is the left-hand side. So it just tells us that f of y will be higher than f of x plus this interval that we get from the tangent line. So, and this characterization is an if and only if characterization, which means that for a continuously differentiable function, if it is convex, then this inequality is satisfied. And on the other hand, if this inequality is satisfied for every pair of points x and y from the set x, then the function f must be convex over the set x. Let's write this characterization again. Let's consider the problem of minimizing f of x, where f is a convex function. This is an unconstrained minimization problem, right? So any points x and y from Rn will actually belong to the feasible set, right? So we are talking about minimizing over x in Rn. This means that from the first order characterization of a convex function, for any pair of points x and y in Rn, we'll have the following. F of y is greater than or equal to f of x plus the gradient of f in x transpose times y minus x. If I find a point x star such that the gradient of f in x star is equal to 0, then for x equal to x star, from this expression here I have f of y is greater than or equal to f of x star, and then here I'll have plus the gradient of f in x star, and the gradient of f in x star is 0, so that's it, right? So f of y is greater than or equal to f of x star for any y. Alright, so but this means that x star is a global minimizer. Okay, so what we established here is that for a convex function which is continuously differentiable, if I want to minimize f of x, then in order to find the global minimizer, all I need to do is to find a point where the gradient is equal to 0. Alright, so we need to just find a stationary point, and then we are guaranteed that this point is the global minimizer for our problem. So this is a great property. Alright, so in general, we only have the property that if a point x star is a minimizer, then the gradient is equal to 0. But in this case, in the convex case, this becomes also a sufficient condition. Alright, so a point is a global minimizer for a convex problem if and only if the gradient of f in x star is equal to 0. This reduces the problem of minimizing f of x for the convex case to the problem of finding a point where the gradient is equal to 0.